All right, welcome back. So this is going to be another lecture on radiation, and we are nearing the end of our course. So let me again stress what I stressed on the last time. Last time around, what we saw was that we looked at potentials and we looked at the cases where we are dealing with non-static charge distributions, and we had this notion of retarded potentials. These are what were the main driving point here was the fact that when you are at a point P which is receiving some electromagnetic radiation from a source at a point say S, so the potentials that you're going to calculate at the point P with if the source S is a distance r away from you, that is going to depend on the the charge distribution at the point S, but it's also going to depend on the if you are at P at some point of time T, the electric field that you measure is going to be a function not of the source at that exact point of time T, but it's going to be the function of what is happening at the source at some retarded time T minus R over C. So this is because it takes electromagnetic news, which of course, as you know very well, travels at the speed of light. It takes it some time to reach the point P from the point S. So everything is going to be delayed by that. To give you an example, if the sun were to extinguish at this moment, here on Earth we will actually take 8 minutes to realize that it has actually gone black, if you wish. So at this point of time, the radiation from the sun that we receive is a function of the light that has started out from the sun 8 minutes before. It takes light 8 minutes to reach us. Similarly, in anything, since there is going to be a finite lag between there's going to be time taken by light to travel a certain distance. All of these will be functions of the retarded time tr. That is what we saw in the last class, and we derived expressions for the potentials and the fields for these non-static distributions, each of which were dependent on this retarded time tr. Okay. So let me again re-emphasize what electromagnetic radiation is. Maxwell's equations allowed for wave solutions. That's electromagnetic radiation or light. The question that we were trying to address is how actually do you generate these waves or from distribution of electric charges. As I said before, we know that a stationary electric charge produces a stationary electric field. If we boost this charge so that it moves at a constant speed, it produces a stationary magnetic field. What we are going to be seeing now is that if we want propagating electromagnetic waves, we actually need to accelerate charges. Okay, so what happens is that when charges accelerate, their fields can transport energy irreversibly out to infinity. This is a process that we are going to call radiation. So in this figure that I have drawn, we are assuming that our source is localized near the origin, and we want to calculate the energy that it's radiating at a time t naught. I've drawn a very large sphere of radius r, and what is going to happen is when we calculate the passing power passing through its surface, this is just the integral of the Poynting vector, right? So P the of r and t is the integral of the Poynting vector and this, of course, as you know, is 1 over mu naught integral of E cross B dot dA. All right. As we said, right now electromagnetic news travels at the speed of light. So this energy actually left the source. So energy left the source at this retarded time. Left source at retarded time T naught equal to T minus R over C. So the power radiated is given by PR let's call it P rad at T naught. This is going to be the limit of R goes to infinity, P R T naught plus R over C. Okay. So this is the energy per unit time that is carried away, never to return. Okay. So let's write this down. Energy per unit time carried away, never to return. Let's say never to come back. Very good. Now let's look at this integral. Okay. Now the area of the sphere is 4 pi r squared. So in order that this integral gives you some finite answer, the Poynting vector must decrease at large r at no faster than 1 over r squared. So for example, if the Poynting vector went as 1 over r cube, then P, the integral of the Poynting vector over dA, will go as 1 over r, and when you take r going to infinity like you need to, this is going to go to 0. Okay. So for radiation to occur, S must decrease no faster than 1 over r squared at large r. This is an important point. Let me write this down. For radiation, S must decrease no faster than 1 over r squared at large r. Right? So this is because, you know, okay, since, let's also write down since the area of sphere is 4 pi r squared, and the integral, and you need to take r goes to infinity. Okay, very good. So now let's think about the static case. Okay, the static case. So what happens there? So if you are looking at the static case, if you're looking at Coulomb's law, for example, electrostatic fields they fall off as 1 over r squared, or faster if the total charge is 0. And the Biot-Savart's law tells us that the magnetic fields, magnetostatic fields also fall off as 1 over r squared, or faster again, if so this is 1 over r squared, and each of this goes as 1 over r squared or faster. So that means that S then goes as 1 over r to the 4, right? Since it's E cross B, it has to go as 1 over r to the 4. Now the area of the sphere, as you know, area of the sphere is 4 pi r squared. This is the thing that we just saw. And therefore, the integral P goes as 1 over r squared. So this goes to 0 as r goes to infinity. Okay, so the conclusion that we get from here is that there is no radiation for static sources. So no radiation for static sources. Now, remember the expressions that we wrote down last time round. So let me so you remember the expressions, you know, this E and B that we had, which generalized the Coulomb's law and the Biot-Savart's law for the non-static cases. So now you see that, you know, for example here, you have things that go as 1 over r, right? So these pieces all go as 1 over r. So if E and B both go as 1 over r, in that case, S goes as 1 over r squared, and P is going to go, you know, there is a 4 pi r squared on top, and there is an 1 over r squared downstairs. So that is going to give you a finite number when you take r goes to r going out to infinity. Okay. All right. Let me get rid of these circles, and let me take you back. So what I wanted to say here is that for non-static sources, non-static cases, time-dependent fields go as 1 over r. So these, you know, so these are terms. So these are terms responsible for radiation. Okay. So let's say that, so now what happens is, so we can summarize by saying that the study of radiation involves picking out the parts of E and B that go as 1 over r at large distances from the source, and constructing from them the 1 over r squared term in S, integrating over a large surface, and then you take the limit of r goes to infinity. Okay, so we are going to look at our first example now, and this is going to be the radiation from an electric dipole, and so this is what we want to do now. Okay, so we have these two small metal balls, if you wish, and spheres which are separated by a distance d and are linked by this fine wire. Okay, now what is happening is that at a time t, the charge on the upper sphere is q of t and the charge on the lower sphere is minus q of t, and we are driving the charge back and forth through the wire from one end to the other at an angular frequency which we will call omega. Okay, so q of t is going to be q naught cosine of omega t. So the result is an electric dipole which actually oscillates. So this is P of t, which is equal to P naught cos omega t, and this is in the z direction. Okay, where P naught is just given as q naught into d. That's the maximum value for the Hammond dipole moment. Now, as you can well understand, the retarded potential that we have. So let's write this here. Retarded potential that is given by V of RT 1 over 4 pi epsilon naught into two terms, q naught cos omega t minus r plus over c by r plus, and I'm not going to be able to fit this in, so let me transport this to the next line. Minus q naught cos omega, that's a cos omega t minus r minus over c by r minus, where r plus minus is given by r squared minus plus r d cos theta plus d over 2 whole squared whole to the half, of course. Now what we are going to do now is we are going to make a series of approximations that makes our life simple. Okay, so the first approximation that we are going to make is we are going to make this physical dipole into a perfect dipole. So we want the separation between these two metal spheres to be extremely small. So this approximation 1, so approximation 1 is d is much less than r. Okay, so if d is much less than r, so remember that if you have have an expansion of 1 plus x whole to the n, and this is approximately equal to 1 plus nx when x is much less than 1, right? See, the higher terms in x squared terms will just drop off. Okay, so we are going to use this approximation in the above. So this essentially yields r plus minus equals to r 1 minus plus d over r cos theta whole to the half, which is equal to, so in the first we have dropped the d square terms. Now we are going to use the expression that I've just showed you above. So this is r1 minus plus d over 2r cos theta. Okay, now 1 over r plus minus is 1 over r into 1 minus plus d over twice r cos theta inverse. Now again you use the approximation that I've just said. 1 plus x whole to the power n goes as 1 plus nx. So the minus 1 comes down. So this just becomes 1 over r1 plus minus. Now we have an extra sign, d over twice r cos theta. Okay, this is going to be useful for us, and we are going to just put this down now to understand how the cosine of this angle that we have written down, how this can be approximated. So cos omega t minus r plus minus over c So writing this down in terms of r plus minus, this is simply cos of omega t minus r over c plus minus omega d by 2c cos theta, and you expand out this in sine and cos of omega t minus r over c cos of omega d by 2c cos theta minus plus sine of omega t minus r over c sine of omega d by 2c cos theta. Very good. So that's just expanding this out. Now we are ready to put in our second approximation. So far what we have done is we have assumed that d is much less than r. So the second approximation that we're going to do is going to say that d is also much less than the wavelength of these waves. So that is going to be approximation 2. Approximation 2 is going to be d is much less than c by omega. If we do this, then our formula simplifies further. Remember that if you have an expansion of sine theta, when theta is small, this goes as theta, and cos of theta when theta is small goes as 1. So this is theta is much less than 1. And in this case, our theta is given by, well, let's not call this theta, let's call this phi. Let me not confuse you. Sine phi goes as phi, cos phi goes as 1 when phi is much less than 1. In this case, phi is given by omega d by 2c cos theta. Okay, this is much less than 1. So the approximations that we're going to have is that cos of omega t minus r plus minus by c, using the approximation 2 now, is going to be approximately equal to cos of omega t minus r over c minus plus omega d by 2c cos theta into sine of omega t minus r over c. Okay, so this is the next approximation that you have used, where we have replaced. So you had this thing here. This is being replaced by 1, and this guy is being replaced by omega d by 2c cos theta. Right, so sine theta is being replaced by theta, cos theta is being replaced by 1. Okay, very good. So that's what this expression is, and now you can plug this into the form of v. So v in this approximation, v of r theta t is given by p naught cos theta by 4 pi epsilon naught r minus omega over c sine theta, sine of omega t minus r over c, plus 1 over r cos of omega t minus r over c. So now this. So one quick thing to check is that if you are looking at for example, if you look at the static limit of omega going to 0, then you just recover v of v, if you wish, is just equal to p naught cos theta by 4 pi epsilon naught r squared. Okay, so you just recover the old formula. And but we are interested in something else here. So we are interested in in what is called the radiation zone. So that is a large distances, interested in fields that survive at large distances from the source. And this is going to be our approximation 3. Okay. Approximation 3, which is r is going to be much greater than c over omega. Okay, I have put this a little too close. I'm just going to get this down. Very good. So now the formula that we have. So with this, what happens is that you can just completely neglect this this cost term that you have out here, because r 1 over r is going to be much less compared to omega over c. That's our approximation. So we drop this term, and so our expression is v of r theta t is going to be minus p naught omega by 4 pi epsilon naught c into cos theta over r sine of omega t minus r over c. So that is our expression. Okay, so that is our expression that we are interested in. So this is the expression for V. All right. Now we also want to determine the vector potential. Vector potential, the first thing that we have to keep in mind is that we need to find out what the electric current flowing through the wire is. Current through the wire is this is just, so you remember these were two dipoles linked, two metallic spheres linked by a fine thread, and since the charge was oscillating, so I that you have is going to I of t is just going to be dq dt, and this is obviously going to be in the z direction because the charge is going up and down the z axis. So this is simply nothing but minus q naught omega sine omega t in the z direction. Very good. Now look at this figure here. What we have is that we are looking at at the field at a point. Let's call this point P, which is at a distance of r from the origin. You need to look at a small line element dz on the z-axis, and you need to find out what the field there is, and you need to integrate this from minus d over 2 to plus d over 2 to get the expression for A, right? So the expression for A is simply A of r t is mu naught over 4 pi integral. Now this integral goes from minus d over 2 to d over 2, and it's just minus q naught omega sine of omega of t minus r by c. This is z cap by r, right? And this is the approximation, where r plus r is just given by r squared minus twice r z cos theta plus z squared, the square root of this. Now remember that we are working in an approximation where, so z takes, so what you're doing is z can go so the integrals integration the limits of the integration are given by d, right? And you also have that d is much less than r. So this essentially amounts to the fact in the first approximation r, this curly r can be approximated as the usual r. So this can be approximated by the distance from the center, if you wish. Okay, very good. So this means that the expression for a is just going to be simply a of rt r theta t is going to be minus mu naught p naught omega by 4 pi r sine of omega t minus r over c into z cap. Very good. Okay, so that is that. Now what we want to do is we want to find out the expressions for the electric field and the magnetic field and so on. So I will not actually go into this. I'll not work them out. I'll just give you the expressions. So this is this, and let me actually just write down these expressions for you. Not write down these expressions for you, but copy them. Okay, so this is simply just this. So the expression for E is given by this. The expression for B is given by this. I mean, this is just straightforward, of course. And B is curl of A. So you have expressions for phi and V, and you have expressions for A. So you can get the expressions for E and B. We want to find out what the Poynting vector is, and for that you need to take the curl of E with B. This is again straightforward. I urge you to sit and just get this done. The important thing is, so for example, the intensity is given by is the average in time over a complete cycle average of S. So let's not confuse you by trying to write I. Let's just write S bar with these angular brackets, and that if you do this, you will get that this is mu naught p naught to the p naught squared omega to the 4 by 32 pi squared c into sine squared theta by r squared r cap. And there is an interesting thing to note here is that there is no radiation along the axis of the dipole where sine theta equal to 0. Okay. Yeah, anyway, so now if you want to find the total power that is radiated, this is found by integrating S, this average of the thing, over a sphere of radius r. So let's call this P. This is integral of S dot dA. This is the thing that we've just found out. So P naught squared omega 4 32, so not 33, 32 pi squared c I need to integrate. There is a sine squared theta over r squared, and there is r squared sine theta d theta d phi. And once you do this, what you get is P is equal to mu naught P naught squared omega to the 4 by 12 pi c. So this is a lot of formulae. So I wanted to emphasize something at the end, that is, that's something that you should take home from this. Notice that the formula for P has an omega to the power 4 dependence. So there is this very strong frequency dependence of this power formula. Interestingly enough, this is what accounts for the blueness of the sky. Sunlight passing through the atmosphere stimulates atoms to oscillate as tiny dipoles. The incident solar radiation covers a broad range of frequencies. That is what is white light. But the energy absorbed and re-radiated by the atmospheric dipoles is going to be stronger at higher frequencies, because this particular form of P that you have seen, there is an omega to the power 4. So this is more intense in the blue, more intense in the blue than in the red. It is this re-radiated light that you see when you look up in the sky, unless if you're just looking at the sun, then it looks at something else. Okay. So, because these electromagnetic waves are transverse, the dipoles oscillate in a plane which is orthogonal to the sun's rays. In this celestial arc, perpendicular to these rays, the blueness is most pronounced. And here the dipoles oscillate along the line of sight, and sending no radiation to the observer. So this is one end of the stick, if you wish. There is another thing that is directly related to this as well. That is the redness of the night sky. Of the redness, not of the night sky, but of the sunset. If the night sky became red, we would all be in deep trouble. Sunlight, when the sun is about to set, sunlight comes in at a tangent to the surface of the earth, and this must pass through a much longer stretch of the atmosphere than, for example, when the sun is straight overhead. So in the same way, the blue will actually be removed by this scattering of the light, and what is actually left behind is the red. Okay, so this is something which is a direct consequence of everything that we see around us. And I just wanted to emphasize the fact that this omega to the power 4 dependence that we have seen is directly responsible for the blueness of the sky in the usual time, and also for the redness of the sunsets or the sunrises. Okay. So that's all for now, and we will get back to the last lecture where we will be doing magnetic and dipole radiation and radiation for an arbitrary source. There was also something about point charges, but I think that is going to take us a little too far, and we will probably wrap up the course with just another lecture. All right then, thank you very much, and I hope this time around the video has sound. If not, well, who knows what will happen. So see you next time. Bye bye.